The landscape for GPU kernel engineering is undergoing a seismic shift that will define the careers of senior engineers by the year 2026. For decades, the path to high-performance computing was paved with deep mastery of low-level C++ templates and intricate CUDA programming. Tools like CUTE programming, too, provided the necessary power to squeeze every ounce of performance out of modern hardware, but they demanded years of specialized syntax training and manual register tiling. Now consider the emerging reality where the barrier to entry is shifting from syntax mastery to orchestration fluency. The question facing the industry is not whether automation will replace manual coding, but how engineers should position themselves within this new workflow. Here is the thing about the current trajectory. Research into systems like CUTLASS, a compact domain-specific language, demonstrates that high-level Python abstractions significantly outperform raw C++ CuTe or CUTLASS when paired with large language model agents. By reducing the reasoning burden on low-level details and incorporating first principles, speed-of-light guidance, these new frameworks achieve speedups of up to 1.68 times over standard PyTorch implementations. This suggests a fundamental change in what skills are actually valuable. Engineers must prioritize DSL fluency and performance-bound reasoning over deep C++ syntax mastery, as automated tools will handle the complex micro-optimizations previously requiring years of expertise. However, this does not mean the old knowledge becomes obsolete. It transforms. The consensus suggests a hybrid future where engineers must master domain-specific languages to effectively direct large language model agents, but they cannot abandon the underlying hardware semantics required to validate performance bounds. Think of it as the difference between a master carpenter and an architect. In the past, the engineer was the carpenter, cutting every beam and joining every joint by hand. In the future, the engineer is the architect, designing the structure and ensuring the materials meet the load requirements, while automated systems handle the physical construction. Consider the specific case of Flash Attention 2 on Nvidia Hopper architecture. While automated tools excel in agent efficiency, studies like Flash Decoding ++ and Kevin highlight that raw library limitations, such as static data flows in CUTLASS and the complexity of iterative reinforcement learning training, still demand deep architectural understanding. Current abstractions may obscure certain performance bottlenecks that only a human with hardware intuition can spot. If you rely entirely on an agent to generate a kernel without understanding the memory hierarchy, you might end up with code that runs but is inefficient in ways the compiler cannot optimize. The role of the large language model inference engineer is evolving from writing raw kernels to orchestrating a workflow where the domain-specific language acts as the interface between high-level model requirements and hardware-specific execution. This effectively makes the C++ CuTe implementation details an internal abstraction managed by AI agents. You are no longer writing the loops. You are defining the constraints and the objectives. You are telling the system what performance envelope you need to hit, and the system uses reinforcement learning feedback loops to iteratively refine kernel performance. This shift requires a new kind of mental model. You must learn the speed-of-light guidance frameworks that allow the domain-specific language to iterate on its own code. Instead of focusing solely on static C++ optimization techniques, you focus on the feedback mechanisms that allow the system to learn from its own execution. This is the future-proofing strategy. If you spend all your time memorizing C++ template metaprogramming syntax, you will find yourself obsolete as automated generation becomes the industry standard. The value lies in your ability to direct the automation, not to replace it. Yet, there is a critical caveat to this automation. The research indicates that while CUTLASS excels in agent efficiency, the complexity of iterative reinforcement learning training still demands deep architectural understanding. You cannot simply write a high-level specification and expect perfect results. You need to understand the semantics of the domain-specific language over manual register tiling. You need to know why a certain fusion strategy might fail on specific hardware generations. This means your learning path should balance DSL fluency with a rigorous understanding of the underlying hardware semantics. Imagine you are building a bridge. The automated tools are the construction crews and the cranes. They are incredibly fast and precise. But if you do not understand the physics of load distribution, you might design a bridge that collapses under stress. The domain-specific language is your blueprint. The large language model is the crew. You are the structural engineer. You need to know the blueprint language fluently, but you also need to know the physics of the materials. This hybrid skill set is what will separate the leaders from the followers in the coming years. The industry is moving towards agentic systems that compress expert knowledge into automated workflows. This is a scalability bottleneck solution. Manual kernel engineering is becoming a bottleneck because there simply are not enough humans with the required depth of expertise to keep up with the pace of hardware evolution. By automating the generation, we can scale the output of high-performance kernels. But the quality of that output depends entirely on the quality of the input, which is where the engineer comes in. So, what should you actually learn? You should prioritize understanding the architectural principles behind fused kernels and the semantics of the domain-specific language over manual register tiling. You should focus on the speed-of-light guidance frameworks and reinforcement learning-based feedback loops that allow the system to iteratively refine kernel performance. You must maintain a strong grasp of hardware semantics to validate performance bounds and debug complex fusion strategies that current abstractions may obscure. The transition is not about abandoning the old skills. It is about elevating them. You are moving from the execution layer to the design layer. You are moving from writing code to defining constraints. This is a more powerful position, but it requires a broader understanding of the entire system. If you focus only on the syntax of the domain-specific language, you will be limited by the capabilities of the agent. If you focus only on the hardware, you will be limited by the pace of automation. The sweet spot is in the intersection. As we look toward 2026, the engineer who thrives will be the one who can speak both languages. They will understand the high-level abstractions that drive the agents, and they will understand the low-level realities that constrain them. They will know when to trust the automation and when to intervene. This is the new standard for GPU kernel development. It is a future where speed is not just about the clock cycles of the processor, but the speed of the iteration loop between human intent and machine execution. The tools are changing, but the need for deep technical insight remains constant. Your job is to adapt that insight to the new tools. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.